Hello everyone. Today we'll discuss about conservation of angular momentum. So now, before starting, let me tell you what is the meaning of conservation. Conservation means remains constant. So now, what does this conservation of angular momentum means? It means for any given system, conservation will always remain constant throughout the system. So now last year you have studied conservation of linear momentum. That was in case of translational motion. Now in this rotational chapter we are only studying the analogous terms. Okay, so means as you know, F is equals to dp by dt leads to conservation of momentum, that is linear momentum, when no external force will act. Unless and until there is no external force, the momentum for that system will remain constant. This is the law of linear conservation which you have studied last year. So similarly now there is an conservation of angular momentum which will be related to the rotating bodies. Now as it is related to rotating body, instead of force there will be the term torque, and this linear momentum will be represented by angular momentum L. Okay, so now d tau is equals to dl by dt leads to conservation of angular momentum. When your angular momentum will be conserved? When no external torques are present on the system. Okay, means unless and until no force act on the given system, the momentum of the system will remain conserved, or you can say constant. Okay, so the law states that, statement is given over here, angular momentum for a rotating body is conserved or remain constant if and only if when your external torque acting on the body is 0. Okay, so now this I will explain you in more details in the examples so that you can get immediately what does it mean. So before that we will now prove this law. Okay, you have to prove this law. So let us start with the derivation. So for this, consider a particle is rotating about an axis with the tau torque, you can say tau, p be the linear momentum of that particle which is of mass m, and r be the position vector. Now by definition of angular momentum which you have seen in last lecture, that is L vector L is equals to vector r cross vector p. Okay, by definition. Now next step what you have to do, differentiate this equation with respect to time. So means what you will do, take its derivative with respect to time. So dl by dt is equals to d by dt of this whole bracket r cross p. Now you will use your UV rule of differentiation. So dl by dt as it is equals to first r as it is, derivative of p, plus p as it is, cross, in between it is cross, you will write cross, derivative of r. Okay, but now dr by dt, r is the position vector, means it is showing you the displacement. So displacement upon times becomes velocity, and according to Newton's second law, force is nothing but rate of change of momentum, linear momentum with respect to time, and definition of linear momentum, p is equals to mv. So this all terms we are going to substitute in this bracket. Instead of this dr by dt you will substitute v, instead of dp by dt you will substitute f, and instead of p you will substitute mv. Okay, so now let us see next step. So therefore what equation you will get, dl by dt is equals to r cross f plus m v cross v. Now you know vector product with itself is a 0. This property you have studied in your 11th standard in scalars and vector chapter. So since cross product of a vector with itself is 0, so here we have v cross v. So this v cross v will become 0, 0 into m will become 0, and f cross f as it is. Now by definition of torque, f cross r is nothing but tau. So you will substitute over here. So therefore what you will get, dl by dt is equals to tau. Okay, now consider one case, if resultant torque acting on the particle becomes 0. Okay, means if we are considering, so then what will happen? Tau becomes 0 means dl by dt becomes 0. That is nothing but L will become constant. How you can write L is constant? Because this is derivative of L, and derivative of L is 0, means constant number. It is a 0. So any quantity whose derivative is 0 means that this quantity is a constant. Okay, so here we have used the property of the derivative. Once again I am telling, any quantity whose derivative is 0 means that quantity is constant. Therefore you can write L is equals to constant. So this is what we have to prove. Means L is constant means what? Angular momentum of the system will remain constant. When it will remain constant? When you will consider your torque acting is 0. Okay, so angular momentum for the system will remain constant only and only when external torque acting on the system is 0. So now let us start with the examples. Now the examples of conservation of angular momentums are ice dancer or acrobat dancers or ballet dancers. These all dancers, or you can say while a person is swimming, okay, in a pool. So these all are using the concept called conservation of angular momentum. Okay, so now here one diagram is shown you, conservation of angular momentum for ice skaters or ice dancers. So now what happens in this case? Now you know this formula, L is equals to I omega, that is the formula for angular momentum. Now see, in this case, in first diagram, when this dancer is rotating about an axis, now where is the axis of rotation? Along this direction. Okay, this will be the axis of rotation. Now when she is rotating, in this case I will be larger, omega will be smaller. Now why so? If the axis of rotation is passing through the center of the dancer, and if she stretches out her hand, so now particle which is over here with respect to this axis of rotation, so this distance becomes larger. And if this distance becomes larger, means what? Her I, you can say that is mr square. So r becomes larger. So square of that distance again become larger. Means what? Your moment of inertia I is larger. Okay. Now just imagine when she rotate with her hand in outward direction, her speed will become less. So here we have written omega becomes small. And in this case, see, axis of rotation is again along the center, along her center, but here I will be small and omega will be large. Why so? Because now here she is folding her hands, so particle is over here, or you can say here. So this distance from this axis of rotation is less as compared to this. Okay, so your distance becomes less, means your r becomes less, so your I becomes less, but her speed will be maximum. Okay, because see, if you see this formula, L is equals to I omega, if you take this omega here, then I is inversely proportional to omega. So when your I will increase, omega will decrease. When your I will decrease, your omega will decrease. So this I and omega, these are inversely proportional. So this is an example, means this ice skaters, or you can say ballet dancers or acrobats, they use this moment of angular moment, concept of this angular momentum, or you can say moment of inertia, to increase or decrease their speed. Okay, now see here, angular momentum before stretching hands will be L1 is equals to I1 omega 1. After stretching will be say L2 I2 omega 2. Now if you use principle of conservation of momentum, angular momentum, so how you can write? L1 is equals to L2, that is nothing but I1 omega 1 is equals to I1 omega 2. Now see, again this is the same condition. If I1 will be less than I2, then omega 2 will be greater than omega 1. Why? Because see, this I1 upon I2 is equal to omega 2 upon omega 1 means I1 and omega 1, these are inversely proportional. So if I1 is less, omega 1 will be greater. That is nothing but this same example. Okay, so this ice skaters or ballet dancers or acrobats, they are using this concept to increase or decrease their speed while they are performing their motion. Okay, then take some another example. This person is sitting on a chair and rotating. This will be the axis of rotation for that person. Now see here, when he outstretches his arms, so that time I will be greater. Again, the particle which is over here, its distance is larger from this axis of rotation, so r is larger, so your I is what? mr square. R is larger, so I is larger, and obviously omega will be less. Okay, imagine just you sit on a chair and rotate. So when you stretch your hands out, your speed will be less, and when you take your hand inside or fold your hands, your omega speed will be larger, and your moment of inertia I will be less, because particle is over here and this is the axis of rotation. So this distance becomes less, and so your r becomes less, that is nothing but your I becomes less, and so moment of inertia becomes less, and then angular speed becomes larger. So this is some another example. Okay.